Hello everyone, we'll discuss valence bond theory. We know that ionic, covalent and coordinate, these are the types of chemical bonds. Amongst these, in case of covalent bonds, for the formation of covalent bonds, different theories we have stated. Electronic theory of valency, valence bond theory, valential electron pair repulsion theory, molecular orbital theory. So amongst these four important theories, today we'll discuss about the valence bond theory. This was stated by scientists Hitler and London, and later on improved by, modified by scientists Pauling and Slater. Okay, many things are credited, or the credit goes to the Linus Pauling, scientist Linus Pauling. In the third decade of the last century, the Linus Pauling stated his theory. About in 1930 he stated his theory. Valence bond theory states that when the atomic orbitals of two different atoms, when these atomic orbitals consist of the unpaired electron with opposite spin, when such atomic orbitals with unpaired electron with opposite spin, when these atomic orbitals overlap together, then there will be a formation of covalent bond. This is the main core part of this theory. For example, first hydrogen atom having one electron in its s orbital, another hydrogen atom having one electron in its s orbital. So what will happen? These two atomic orbitals overlap together and there will be a formation of covalent bond. S orbital of first hydrogen, s orbital of another hydrogen, they are merging together. So in this way the overlapping of atomic orbitals result in the formation of covalent bond. First thing. Next thing is extent of overlapping is directly proportional to the strength of covalent bond. Means what? Greater the extent of overlapping between the atomic orbitals of the different atoms, then more will be the strength of the covalent bond formed between them. One more thing is the extent of overlapping should not be greater than 50%. Okay, now there is a certain limit so as to get merged, so as to get overlapped between these two atomic orbitals, because we know that in an atom there is a nucleus and around the nucleus electrons are revolving. The different forces are existed there. In between two nuclei of the atoms there is a force of repulsion. Both nuclei are the positively charged. In between electrons, outer shell electrons of both the atoms or atomic orbitals, there is also repulsion. So repulsive forces also exist. Besides this, attractive forces are also there. Nucleus of first atom attracts the electron of another one, nucleus of the second one attracts the electron of first one. So that is also there. So if the extent of overlapping is greater than 50%, what will happen? The magnitude of repulsive forces will be increased. So in that case bond formation will not take place. Then the strength of bond, strongness of bond is also related with the directional nature of the atomic orbitals which will be merged. We know that s orbital is spherically symmetrical. It is known as it's a non-directional orbital, and p orbital is a directional one. Okay, at a certain specific direction or the certain specific axis, the probability of finding of electron for the p orbital is maximum. Suppose here I draw the px orbital, means what? Probability of finding an electron is maximum over the x-axis for this px orbital. Say py orbital we are discussing. In this case the probability of finding an electron is maximum over the y-axis. Here the pz orbital means what? Probability of finding an electron is maximum over the z-axis. Means what? P orbitals are the directional one. Okay. Besides that, the d orbitals are also there. dxy, dyz, dx square, y square, dz square. All these orbitals, their shapes you can see in the video of the atomic structure. Okay. So p, d, f, these orbitals are directional in nature. S orbital is a non-directional in nature. Why we are calling it non-directional? Because this electron in the s orbital can form bond everywhere. Means suppose the another orbital approaches from the left side, here that electron may form bond. If the another orbital approaches from the upper side, lower side, downside, or in any side, if the another species approaches, another orbital approaches, in that direction it can form. So the bond formation is not towards any specific direction in case of s orbital. That's why it's a non-directional. So what is the main thing here? If the orbitals are get overlap together and both orbitals are the s orbitals. For example, s orbital of one atom, s orbital of another atom. So s and s both are the non-directional orbitals. So whatever the bond will be formed, that bond is comparatively weak bond will be formed. Suppose s orbital of one atom and p orbital of the another atom, if there is a formation of bond, in this case one orbital is non-directional and the p orbital here is the directional one. So in this case the bond is slightly stronger. Okay, the bond which is formed by the sp overlap is slightly stronger one. And suppose the third possibility, the bond is formed between the two p orbitals. Okay, now p orbital of one atom, p orbital of another atom, if they are overlapping axially like this. This is the p orbital of first atom, this is the p orbital of another atom, and the overlapping occurs. Okay, so here whatever the bond is formed, it is the most strong bond amongst these three cases, because this is p orbital is directional, here the another p orbital is also directional one. Okay, so this is about the how the bond formation takes place, overlapping, extent of overlapping, strongness of bond. Okay, and students see, if it depends upon the type of overlapping. Two possibilities are there. The overlapping may takes place either axially. Okay, I'll clean it and I'll tell you about the types of overlapping. The overlapping may takes place either axially, we call it as an axial overlap, or the axial overlap, or the end to end overlap, or the head on overlap. This is the first type of overlap. And the another type of overlap is it's a parallel or sidewise or lateral overlap. Now in this case what happens? Axial or end to end or head on overlap is nothing but here the first atom, its orbital, another atom is, suppose its orbital is p orbital, and if they merge together, s orbital of one atom, p orbital of another atom, if the overlapping occurs. So in this case, both the nuclei of the atoms and both the electrons, they are in the one axis only. That's why we call it as there is a formation of sigma bond. Okay, there is a formation of sigma bond. Yeah, just okay. We'll continue. The overlapping which is formed axially, this type of overlapping we call it as axial, end to end or head on overlapping, where both the nuclei and electrons which are get overlapped are in one axis. Okay, so it may occur between p orbital or s, okay, or sometimes d orbital may be involved here in this case. Another type of overlapping is the sidewise parallel or lateral overlapping. Suppose we have a py orbital of one atom, py orbital of the another atom, and if both consist of the unpaired electron with opposite spin, so in that case these orbitals merge together, come closer, and then there will be a formation of a pi bond. Okay, now generally we are showing representing it like this, but these two orbitals come closer and here there will be a formation now of the pi bond. Okay, now actually here we are learning this type of overlapping, we call it as a parallel, sidewise or lateral overlapping. Parallel, sidewise or lateral overlapping result in the formation of pi bond. We are representing it like this. Okay, and here both the nuclei and electrons, they are not in the one plane, they are in the different plane. Okay, now students, the next thing is the type of bond. Here I told you this type of overlapping result in the formation of pi bond. Here this type of overlapping means axial, end to end or head on overlapping result in the formation of sigma bond. Okay, then the sigma bond and pi bond, that points of differentiation we need to know. Okay, now then will be a bulk explanation will be over. So what is the sigma bond? Sigma bond is a bond, it is a type of covalent bond which is formed by the axial overlapping of atomic orbitals. And what is the pi bond? Pi bond is a bond which is formed by the parallel overlapping of the atomic orbitals. Okay, now by this representation few minutes back I told you what is axial and what is the parallel or lateral overlapping of atomic orbitals. Second thing, sigma bond is a strong bond and pi bond is a weak bond. Sigma, why it is strong? Because it is formed by the axial overlapping of the atomic orbitals. Okay, face to face, end to end, head on overlapping is there. So that's why the nucleus of both the atoms, they are pulling electron towards themselves. okay now, and the strongness is there in between that in that bond, okay. But here what happens in case of pi bond, it is a sidewise overlapping, because nucleus is in one axis, electrons are in the another axis, okay. So there is not a strongness in the bond and it's a weak bond. Next thing is sigma bond is represented like this and the pi bond is represented like this, okay. Sign I showed. Sigma bond is less reactive bond and the pi bond is the more reactive bond, okay, or highly reactive bond. Why? See, here we have a molecule and in that molecule suppose there is a sigma bond. So what happens when that molecule react with the another species? In that case, as the sigma bond is strong bond, sigma electrons does not take part in the chemical reaction with the another species, okay, because these electrons are strongly involved in a bond formation. Here what happens, pi bond is a weak bond. When the reaction occurs of the molecule with the pi bond with the another species, what will happen? That as the pi electrons are the weak electrons, they take part in a bond formation, they take part in the reaction with the another species easily, okay. Now easily these electrons are available because pi electrons are the pi bond is weak bond, that's why pi electrons can take part in a chemical reaction with another species easily, that's why it is more reactive. Now one more thing is free rotation of atoms around the sigma bond is possible. Free rotation of the atoms around the sigma bond is possible. Here in this case, free rotation of atoms around the pi bond is not possible. What is the meaning of free rotation? See, whenever the multiple bonds are to be formed, in that case the first bond is sigma bond and the another bonds are the pi bond, okay. It is sigma bond is just similar to the skeleton in the animals, okay. Basic skeleton determines about, it gives the basic general idea about the external structure of that organism. In the same way, sigma first bond is the sigma bond, okay, and around the sigma bond the other atoms can be moved, okay. It is just similar to the, say for example, basic skeleton of human being, and in the basic skeleton I can rotate here, my neck I can rotate, my hand I can rotate, okay now. In the same way, around the sigma bond the other atoms can be moved, okay. Free rotation of the other atoms is possible. But tell me, around the pi bond, is it possible? It is comparable with the, suppose someone's neck or head is kept as it is and it is said, rotate freely your body, complete body. Is it possible? Or keep steady your hand as it is and rotate your whole body. Is it possible? No, it is not possible. In the same way, around the sigma bond free rotation of the other atoms is possible. Around the pi bond free rotation of the atoms is not possible. We will see few examples. Now the sigma bond, these few points of differentiation I told, pi bonds few points of differentiation I told, okay. Which type of overlapping, strongness, and these are the adequate things here. In case of sigma bond, the 80 kilocalorie per mole, this much energy or greater than 80 kilocalorie per mole energy is required to break the sigma bond. For the pi bond, so as to break the pi bond, 65 kilocalorie per mole or less than 65 kilocalorie per mole, that much energy is required to the pi bond, okay. Now these are the general things. Let's have a few examples. Hydrocarbons we know. I'll take an example of alkane, alkene and alkyne. For example, we have a ethane. Ethane chemical formula C2H6. Here its structural formula is like this. 2 carbon atoms and total 6 hydrogen atoms are there. Here 1, 2, 3, 4, 5, 6 and 7. 7 sigma bonds are present. There are the total 7 sigma bonds. And here we have a ethene. So in case of ethene, here we have a C2H4 is the ethene. So its structure is like this: C double bond C and H4, C2H4. Now here, whenever there is a single bond between two atoms, it's a sigma bond. Whenever there is a multiple bonds, say in between 2 carbon atoms, there is a double bond now. So in that case, first bond is sigma, second bond is the pi bond always. First bond is alone, pi bond can't exist, okay. There must be a sigma bond and later on there may be a pi bond, but alone sigma bond can't, alone pi bond can't exist, alone sigma bond can exist. Say for example, we have a ethine, which is also known as acetylene, C2H2. In this case, C triple bond CHH, like that the structure is. So in between carbon and hydrogen, the bond is which one? In between carbon and hydrogen, the bond is sigma. Here also sigma, and here the triple bond is there, first sigma and 2 pi, first sigma and 2 pi. Okay. So the first bond is sigma and the other bonds are the pi bonds. Okay. Now, what are the limitations of valence bond theory? Limitation is that it doesn't explain the tetravalency of carbon, because valence bond theory, that overlapping of atomic orbitals, there should be an unpaired electron, but we know that in case of carbon, its electronic configuration is 1s2, 2s2, 2p2. Am I correct? Carbon, its electronic configuration is 1s2, 2s2, 2p2. Carbon having only 2 electrons, 2 unpaired electrons in the valence shell. So according to this theory, carbon should form only 2 covalent bonds, but practically we are seeing carbon is a tetravalent. So the tetravalency of carbon is not explained here. Okay, and it doesn't explain the geometry of the molecule. Okay, and it consider that electron density is concentrated in certain specific region. In the orbital, electron densities get concentrated, but the modern theories proves that electron density is not concentrated in a certain specific region. Okay, so it doesn't tell us about the color of compound, magnetism of compound. Okay, the compound is magnetic or not, that also limitations we can put here, but it is one of the good theory. It gives idea about the chemical bonding. Later on, the valence shell electron pair repulsion theory, hybridization, molecular orbital theory, these theories gives the further clarity about the covalent bonding and its characteristic. Okay, thank you for watching. Bye.